Hello everyone, welcome back to me learning Rust after a small vacation. We stopped at chapter 10, chapter 10, just before the lifetimes. So let's continue. Lifetimes are another kind of generic that we've already been using. Rather than ensuring that a type has the behavior we want, lifetimes ensure that references are valid as long as we need them to be. One detail we didn't discuss in the reference and borrowing section in chapter 4 is that every reference in Rust has a lifetime, which is the scope for which that reference is valid. Most of the time, lifetimes are implicit and inferred. Just like most of the time, types are inferred. We only must annotate types when multiple types are possible. In a similar way, we must annotate lifetimes when the lifetimes of references could be related to a few different ways. Rust requires us to annotate the relationship using generic lifetimes parameters to ensure the actual references used at runtime will definitely be valid. Annotating lifetimes is not even a concept most other programming languages have, so this is going to feel unfamiliar. Although we won't cover lifetimes in their entirety in this chapter, we'll discuss common ways you might encounter lifetimes syntax so you can get comfortable with the concept. Go. Preventing dangling reference with lifetimes. The main aim of lifetimes is to prevent dangling references, which cause a problem to reference data other than the data it's intended to reference. Consider the program in listing 1016, which has an outer scope and an inner scope. Okay, we have this R, we do an X and then put a reference of X to R, then X goes out of scope, and then we try to print it, and that will be an error, of course. Note that examples listing 16, 17, and 23 declare variables without giving them an initial value, so the variable name exists in the outer scope. At first glance, this might appear to be in conflict with Rust's having no null values. However, we try to use a variable before giving it a value, we'll get a compile time error, which shows that Rust indeed does not allow null values. Okay, so basically, like if I'm doing something like this, let's delete. Here we have let x without a type even. Then I'll try to print line x, something like this. This is going to be an error. Oh, sorry. Like this. This is going to be an error, I guess. Okay, x. Okay. Tap and annotation needed. Okay. So I'm going to do this. X equals 15. Okay, now it knows that x is I32, but I try to print it before it's assigned, so it's an error. And if I do this is no longer an error and actually will work. Yep. Excellent. Okay, the outer scope declares a variable named R with no initial value, and the inner scope declares a variable named X with initial value of 5 inside the inner scope. We attempt to set the value of R as a reference to X, then the inner scope ends and we attempt to print the value R. This code won't compile because the value R is referring to has gone out of scope before we try to use it. Here's the error message. Borrowed value does not live long enough. Okay. The variable x doesn't live long enough. The reason is that x will be out of scope when the inner scope ends on line 7. But R is still valid for the other scope because its scope is larger. We say that it lives longer. If Rust allowed this code to work, R would be referencing a memory that was deallocated when x went out of scope, and anything we try to do with R won't work correctly. So how does Rust determine that the code is invalid? It uses a borrow checker. Okay, the borrow checker. The Rust compiler has a borrow checker that compares scopes to determine whether all borrows are valid. Listing 17 showed the same code as listing 16, but with annotation showing the lifetimes of the variables. So we have like a tag of R is valid here, and the B tag is okay. Let's just read on. Here we announce the lifetime of R with the A has the lifetime of X with B. As you can see, the inner B block is much smaller than the outer A lifetime block. At compile time, Rust compares the size of the two lifetimes and sees that R has a lifetime of A, but that it refers to a memory with a lifetime of B. The program is rejected because B is shorter than A. The subject of the reference doesn't live long as the reference. Listing A18 fixes the code so it doesn't have a dangling reference and compiles without any errors. Okay, so basically, yeah. Now this is the scope of X. Of R, and this is scope of X. Scope of X is larger than scope of R, so everything is okay. Here X, the lifetime B, which is in this case is larger than A. That means R can reference X because Rust knows that the reference R will always be valid while X is valid. Now that you know where the lifetimes of reference are and how Rust analyzes lifetimes to ensure references will always be valid, let's explore generic lifetimes of parameters and return values in the context of functions. Okay, we'll write a function that returns the longer of two string slices. This function will take two string slices and return a single string slice. After we've implemented the longest function, the code in listing 19 should print the longest string as ABCD. Okay, so we have copy it. See if there's any errors here. No. Yeah, we don't have the function longest. I will copy it later, but we basically have string 1, string 2, which is like the first one is 4 characters, the second is 3 characters. Now we do the longest, and we get a result and we print it. Okay. Note that we want the function to take string slices, which are references rather than strings, because we don't want the longest function to take ownership of its parameters. Refer to the string slices as parameters section in chapter 4 for more discussion about why the parameters we use in listing 19 are the ones we want. Okay, so basically we understand why. Because if we create a string and the function takes ownership, we'll have to return ownership. I think it's like possible to do it, and we'll try to do it, but let's actually try to do it now. Yeah, if we just take strings, create a function longest, we take just a string and y, which is a string, and it returns a string, and then I'm just if xlen is greater than ylen, we just have x, and else we just have y. This is the function, and let's just do this. Let string 2 equals string from x, y, and z. So now we have two strings, and if I do let result equals longest x and y, it's string 1 and string 2. So now it looks okay, and maybe I can even run it, and the longest string is ABCD, so everything looks okay. And I think like what happens is that the longest takes ownership of both of these. They're no longer valid. Like if I try to print something like this, it's going to be an error. String 1, right? Yeah. Or string 2. It's an error. These strings are no longer valid, like the string 1 and string 2, because the longest takes ownership, and then it returns one of them. So the ownership of the longest string is passed down to the result. Now let's revert everything here and continue with the example. Okay, so if we try to implement the longest function as shown in listing 1020, it won't compile. Let's just copy and paste. and we see it doesn't compile because it returns reference, and the function's return type contains a borrowed value, but the signature does not say whatever it borrowed from X or from Y. Okay, it's really detailed. Consider introducing a named lifetime parameter. Okay, so I guess we'll do that. Instead, we get this following error. Okay, we got a different error. Expected name lifetime parameter. Is this the error? Missing lifetime specifier. Well, I guess we're just using a different version of Rust. Okay, let's just try to run it and maybe get us something more. Wait. Okay, so we have missing lifetime parameter, an expected lifetime parameter. Okay, so it's just the LSP here is different. So this is the error we get, very, very similar. And it suggests doing this, putting like a lifetime here or something. We'll read about this, I guess. Okay, let's go. The help text reveals that the return type needs a generic lifetime parameter on it because Rust can't tell whenever the reference being returned refers to X or Y. Actually, we don't know either because the if block in the body of this function returns a reference to X and the else block returns a reference to Y. When we are defining this function, we don't know the concrete values that will be passed into this function, so we don't know whatever the if case or the else case will execute. We also know the concrete lifetimes of the reference that will be passed in, so we can't look at the scopes as we did in listing 17 and 18 to determine whatever reference will return will always be valid. The borrow checker can't determine this either because it doesn't know how the lifetimes of X and Y relate to the lifetime of return value. To fix this error, we'll add a generic lifetime parameter that defines the relationship between the reference so the borrow checker can perform this analysis. Okay, let's see. Lifetime annotations don't change how long any of the references live. Rather, they describe the relationship of the lifetimes of multiple references to each other without affecting the lifetimes. Just as functions can accept any type when the signature specifies a generic type parameter, functions can accept reference with any lifetime by specifying a generic lifetime parameter. Lifetime annotations have a slightly unusual syntax. The name of a lifetime parameter must start with an apostrophe, and are usually all lowercase and very short, like generic types. Most people use the name A. For the first lifetime annotation, we place a lifetime parameter annotation after the ampersand of a reference using a space to separate the annotation from the reference type. Here are some examples. A reference of an I32 without a lifetime, a reference to an I32 that has a lifetime parameter named A, and a mutable reference to I32 that also has a lifetime A. Okay, so lifetimes comes, yeah, okay. Just here. One lifetime annotation by itself doesn't have much meaning because the annotations are meant to tell Rust how generic lifetimes parameter of multiple reference relate to each other. Let's examine how the lifetime annotation relate to each other than the context of the longest function. Okay, lifetime annotation in the function signature. To use lifetime annotation in the function signature, we need to declare the generic lifetime parameters inside angle brackets between the function name and the parameter list, just as we did with generic type parameters. We want the signature to express the following constraint. The returned reference will be valid as long as both of the parameters are valid. This is the relationship between lifetimes of the parameters and the return value. We'll name the lifetime A and then add it to each of the reference as shown in listing 21. So basically we define, I guess, that like the generic lifetime, and then we say that this should be of this lifetime, and also the Y will be of this lifetime, and the return type is also of this lifetime, and then everything should work. Yeah, and if we run, we're getting, yeah, the longest string is ABCD. So I'm guessing that, like we read before, that this does not change the lifetime, but I think it ensures that the it will only take parameters like X and Y with the same lifetime. So let's try something. If I'm doing this, yeah, And I'm not even going to try to break it. This is the same lifetime. Sorry. So it still works. So these ones have different lifetimes. Okay, maybe this one. Okay, so we're talking string 1. Let's just do this for a second. I want to see like if this will be an error. No, not an error. So even though these two have different lifetimes, let me just revert it, have different lifetimes, this is acceptable. Maybe and if I'm doing this, okay, sorry, this. Okay, so this is, cannot find, okay, cannot find the, okay, wait. So let's just read on and see why it accepts when we have different lifetimes here. The code should compile and produce the result. Okay, the function signature now tells Rust that for some lifetime a, the function takes two parameters, both of which are string slices that live at least as long as lifetime a. Okay, so this means at least as long as lifetime a. Okay. This function signature also tells Rust that the string slice returned from the function will live at least as long as lifetime a. In practice, it means that the lifetime of the reference returned by the longest function is the same as the smaller of the lifetimes of the values referred to by the function arguments. These relationships are what we want Rust to use when analyzing the code. Remember, when we specify the lifetime parameters in this first signature, we're not changing the lifetimes of any values passed in or returned. Rather, we're specifying that the borrow checker should reject any values that don't adhere to those constraints. Note that the longest function doesn't need to know exactly how long x and y will live, only that some scope can be substituted for a that will satisfy the signature. Okay. And when so the lifetime of this is not coming here, like this is a substitute. This lifetime represents the shortest lifetime relevant for this function, for maybe for this instance of the function even. When annotating lifetimes in functions, the annotations go to the function's signature, not in the function body. The lifetime annotations become part of the contract of the function, much like the types of the signature. Having function signature containing the lifetime contract means the analysis the Rust compiler does can be simpler. If there's a problem with the way function is annotated, the way it's called, the compiler errors can point to the part of our code and the constraints more precisely. If instead the Rust compiler made more inferences about what we intend the relationship of the lifetimes to be, the compiler might only be able to point to a use of our code many steps away from the cause of the problem. When we pass concrete reference to longest, the concrete lifetime that is substituted for a is the part of the scope of x that overlaps with the scope of y. In other words, the generic lifetime a will get the concrete lifetime that is equal to the smaller of the lifetimes of x and y. Because we have annotated the returned reference with the same lifetime parameter a, the returned reference will also be valid for the length of the smaller of the lifetimes of x and y. Let's look at how the lifetime annotation restricts longest function by passing in references that have different concrete lifetimes, listing 10, 12. Okay, so this is what we tried to do, basically, and it works. Okay, in this example, string is valid until the end of the outer scope, string 2 is valid until the end of the inner scope, and result reference something that is valid until the end of the inner scope. Run this code and you'll see that the borrow checker approves. It will compile and print the longest string. Okay, so next let's try an example that shows the lifetime of the reference in result must be in the smaller lifetime of the two arguments. We'll move the declaration of the result variable outside the inner scope, but leave the assignment of the value to the result variable inside the scope with string 2. Then we'll move the print line that uses result to outside of the inner scope after the inner scope has ended. Okay, so basically they defined, it's very similar to what you did before, but they define the result here, and it will still say like it's not in scope because it was assigned here and it's no longer valid. And this is the error. A borrowed value does not live long enough. Okay. The error shows that the result to be valid for the print line statement, string 2 would need to be valid until the end of the outer scope. Rust knows this because we annotate the lifetimes of the function parameters and return values using the same lifetime parameter a. As humans, we can look at this code and see that string 1 is longer than string 2, and therefore result will contain the reference to string 1 because string 1 has not gone out of scope yet. Reference to string 1 will still be valid for the print line statement. However, the compiler can't see that the reference is valid in this case. We've told Rust that the lifetime of the reference returned by the longest function is the same as the smaller of the lifetimes of the reference passed in. Therefore, the borrow checker disallowed the code, listing 23 as possibly having an invalid reference. Try designing more experiments that will vary the values and lifetimes of the reference passed into the longest function and how the return reference is used. Make hypotheses about whether or not your experiments will pass the borrow checker before you compile. And then check to see if you're right. Okay. Thinking in terms of lifetimes. Are we on time? Okay, good. The way in which you need to specify lifetime parameters depends on what your function is doing. For example, if we change the implementation of the longest function to always return the first parameter rather than the longest string slice, we wouldn't need to specify a lifetime on the y parameter. The following code will compile. Okay, we've specified a lifetime parameter a for the parameter x and then return type, but not for the parameter y because the lifetime of y doesn't have any relationship with the timeline of x or return value. Well, that makes sense. When returning a reference from a function, the lifetime parameter for the return type needs to match the lifetime parameter of one of the parameters. If the reference return does not refer to one of the parameters, it must refer to a value created within the function. However, this would be a dangling reference because the value will go out of scope at the end of the function. Consider this attempted implementation of the longest function that won't compile. So we create a string and then we return a slice of the string. Yeah, so by the time this leaves, like the scope is outside, this is no longer valid. That means that the slice is no longer valid. Makes sense. Here, even though we've specified the lifetime parameter a for the return type, this implementation will fail to compile because the return value lifetime is not related to the lifetime of the parameter at all. Here is the error message we get. And okay. The problem is that result goes out of scope and gets cleaned up at the end of the longest function. We're also trying to return a reference to a result from the function. There is no way we can specify lifetime parameters that would change the dangling reference, and Rust won't let us create a dangling reference. In this case, the best fix would be to return an owned data type rather than a reference, so the calling function is then responsible for cleaning up the value, like we did like the first longest that has strings and not slices with the input. Ultimately, lifetime syntax is about connecting the lifetimes of various parameters and return values of functions. Once they're connected, Rust has enough information to allow memory-safe operations and disallow operations that would create dangling pointers or otherwise violate memory safety. Okay, lifetime annotation in struct definitions. So far, the structs we've defined all hold own types. We can define structs to hold references, but in that case, we would need to add a lifetime annotation on every reference in the struct's definition, listing 24, as a struct name important excerpt that holds a string slice. Okay, then we have something like this, very similar to the function definition that we had here, and now this is a type of this lifetime. The struct has a single field part that holds a string slice, which is a reference. As with the generic data type, we declare the name of the generic lifetime parameter inside angle brackets after the name of the struct, so we can use the lifetime parameter in the body of the struct definition. This annotation means an instance of important excerpt can outlive the reference it holds in its part field. the main function here creates an instance of the important excerpt. I think here, yeah. The data in novel exists before the important excerpt instance is created. In addition, novel doesn't go out of scope until after the important excerpt goes out of scope, so the reference in the important excerpt is still valid. Okay, yeah, so yeah, we have the first sentence here that we get as a reference from this novel. Then we just put it here, and then it means that the lifetime of this should be the lifetime of this, and it's the same lifetime that ends here, like on this bracket, curly bracket. Okay, makes sense. Lifetime elision. You've learned that every reference has a lifetime and that you need to specify lifetime parameters for function or structs that use reference. However, in chapter 4, we had a function in listing 9, shows again in listing 25 that compiled without lifetime annotations for the first word. Okay. The reason this function compiles without lifetime annotation is historical. In early version, pre-1 of Rust, the code wouldn't have compiled because every reference needed an explicit lifetime. At that time, the function signature would have to be written like this. Like lifetime, lifetime, lifetime. After writing a lot of Rust code, the Rust team found that Rust programmers were entering the same lifetime annotation over and over and over in a particular situation. This situation were predictable and followed a few deterministic patterns. The developers programmed these patterns into the compiler's code, so the borrow checker could infer the lifetimes in this situation and would need explicit annotation. The piece of Rust history is relevant because it's possible that more deterministic patterns will emerge and be added to the compiler. In the future, even fewer lifetime annotation might be required. The patterns programmed into Rust's analysis of reference are called lifetime elision rules. These aren't rules for programmers to follow. They're a set of particular cases that the compiler will consider, and if your code fits these cases, you don't need to write the lifetimes explicitly. The elision rules don't provide full inference. If Rust deterministically applies their rules, but there is still ambiguity as to what lifetimes the reference have, the compiler won't guess what the lifetime of the remaining reference should be. Instead of guessing, the compiler will give you an error that you can resolve by adding the lifetime annotations. Okay, lifetimes on functions or method parameters are called input lifetimes, and lifetimes on return values are called output lifetimes. The compiler uses 3 rules to figure out lifetimes of the reference when there aren't explicit annotations. The first rule applies to input lifetimes, and the second and third rule apply to output lifetimes. If the compiler gets to the end of the 3 rules and there's still reference for which it can't figure out lifetimes, the compiler will stop with an error. The rules apply to function definition as well as implementation blocks. The first rule is that the compiler assigns a lifetime parameter to each parameter that's a reference. In other words, a function with 1 parameter gets 1 lifetime parameter, A. A function with 2 parameters gets 2 separate lifetime parameters, A, B, etc. The second rule is that if there is exactly 1 input lifetime parameter, that lifetime is assigned to all output lifetime parameters. Okay, the third rule is that if there are multiple input lifetime parameters, but one of them is self or mutable self, because this is a method, the life of self is assigned to all output lifetime parameters. This third rule makes method much nicer to read and write because fewer symbols are necessary. Now let's pretend we're the compiler. Let's pretend we're the compiler. We'll apply these rules to figure out the lifetimes of the references in the signature of the first word function in listing 25. The signature starts without any lifetime associated with the reference. Then the compiler applies the first rule, which specifies that each parameter gets its own lifetime. If 1 parameter gets an A. The second rule applies there exactly 1 input lifetime. The second rule specifies that the lifetime of one of the input parameters gets assigned to the output lifetime. So the signature is like this. Now all the references in this function signature have lifetimes, and the compiler can continue its analysis without needing the programmer to annotate the lifetime in the function signatures. Let's look at another example, this time using the longest function that had no lifetime parameters. Okay, this one. Let's apply the first rule, so we get an A and a B. Okay, you can see that the second rule doesn't apply because there is more than 1 input lifetime. Third rule doesn't apply either because longest is a function rather than a method, so none of the parameters are self. After working through all three rules, we still haven't figured out what the return type's lifetime is. This is why we got an error trying to compile the code in listing 20. The compiler worked through the lifetime elision rules but still couldn't figure out all the lifetimes of the reference in the signature. Because the third rule really only applies in the method signatures, we'll look at lifetime in that context next to see why the third rule means we don't have to annotate lifetimes in this method signature very often. Okay, we've implemented methods on a struct with the lifetimes. We use the same syntax as generic type parameters shown in listing 11. Where we declare and use the lifetime parameters depends on whatever they're related to the struct fields or the method parameters and return values. Lifetime names for struct fields always need to be declared after the implementation keyword and then used after the struct's name, because those lifetimes are part of the struct's type. Okay, in method signatures inside the implementation blocks, references might be tied to the lifetime of reference in the struct field, or they might be independent. In addition, the lifetime elision rules often make it that lifetime annotations are necessary in method signatures. Let's look at some examples using the struct name important excerpt that we define in listing 24. First, we'll use a named method level whose only parameter is reference to self and whose return value is i32, which is not referencing anything. So we have this should compile, and we have a lifetime here. Okay, yeah, because the struct must have a lifetime. The lifetime parameter declaration after the implementation and its use after the type name are required, but we're not required to annotate the lifetime of the reference to self because of this first elision rule. Here is an example of where the third lifetime elision rule applies. So we have self, we have announcement, and we return self. So we print it, we're not using it. This reference, it's not valid, it's not relevant anymore, and we return self. So I guess it puts the A here and here. Basically, there are two input lifetimes, so Rust applies the first lifetime elision rule and gives both self and announcement their own lifetimes. Then, because one of the parameters is self, the return type gets the lifetime of self, and all lifetime have been accounted for. The static lifetime. One special lifetime we need to discuss is static, which denotes that the affected reference can live for the entire duration of the program. All strings literal have the static lifetime, which we can annotate as follows. The text of the string is stored directly in the program's binary, which is always available. Therefore, the lifetime of all string literals is static. You might see suggestions to use static lifetime in error messages, but before specifying static as the lifetime for reference, think about whatever the reference you have actually lives the entire lifetime of your program or not, and whatever you want it to. Most of the time, an error message suggests the static lifetime results from attempting to create a dangling reference or mismatch of the available lifetimes. In such cases, the solution is fixing those problems, not specifying the static lifetime. Okay, generic parameters, trade bounds, and lifetimes together. Let's briefly look at the syntax of specifying generic type parameters, trade bounds, and lifetimes all in one function. Okay, so we have the display, we have longest with an announcement, so it has a type, and it has a lifetime here. And we have the same lifetime of x and y, and the announcement, which is different type, and we print the announcement, and then we return the value. Yeah, it makes sense because this one is not relevant in any way. It just uses it and then tosses it away, this reference, so it doesn't matter here. Everything looks pretty much clear, but this is the longest function from listing 21, and that returns the longer of two string slices, but now with an extra parameter named n, which is generic type t, which can be filled by any type that implements the display trait as specified by the where clause. Yeah, so we have this thing. We think one of the chapters we learned that we can do this instead of adding it here, like t that implements display. This extra parameter will be printed using the curly brackets, which is why the display trait bound is necessary, because the lifetime are type of generic, the declaration of the lifetime parameter a and the generic type t go in the same list inside the angle brackets after the function name. Okay. We covered a lot in this chapter. Now that you know about generic type parameters, traits and trait bounds, and generic lifetime parameters, when you're ready to write code without repetition that works in many different situations. Generic types parameters let you apply the code to different types, traits, and trait bounds. Ensure that even though the types are generic, they'll have the behavior the code needs. You learn how to use lifetime annotations to ensure that this flexible code won't have any dangling references. And all of this analysis happens to at compile time, which doesn't affect runtime performance. Believe it or not, there is much more to learn on the topics we discussed in this chapter. Chapter 17 discusses trait objects, which are another way to use trait. Those are more complex scenarios involving lifetime annotation that we'll only need in very advanced scenarios. For those, you should read the Rust reference, but next you learn how to write tests in Rust so you can make sure your code works the way it should. Well, yeah, lifetimes was really a lot to take in, but I think that basically it's just some connection you have to annotate. I guess we'll just look at the errors we are getting while writing code, and then we can maybe have some sort of intuition about how to arrange the lifetimes correctly. I think we'll try to avoid the static lifetime as much as possible. And next time, I think we'll do tests. So, bye. See you.